Okay, folks, let's get started. So, first thing I want to just remind you of, I saw a handful of folks there last night, but if you didn't yet go see the mummy that's in Upson Lounge, go check it out. It's really cool. There's an exhibition going on in the Upson Lounge right now that is showcasing an ancient Egyptian ibis mummy and talking about the story of this particular ibis and its connection to Cornell. It's really interesting. It also features a digital representation of the mummy that was generated by ECE student Jack DeFay and myself. And the archaeologist that's putting the whole thing on is my wife. So I'd really appreciate it if you'd go check it out and then take the little survey at the end to talk about how the experience was. It'll be in Upson Lounge all day today until 7 p.m. and then 9 a.m. to 7 p.m. tomorrow and Sunday. So if you're around, drop by and check it out. It's really, really cool. Yeah?
What's inside of it?
So what's inside of it is an ibis bird. Let me show you. Let's see. It is an African sacred ibis. One of these. Which you can go to the exhibition to learn about this, but I'll just give you the really brief cliff notes. There are millions and millions of examples of mummies of African sacred ibises. They were mummified as votives to the god Thoth. So in the same way that folks might go into a church and light a candle as sort of a symbolic gesture, folks would offer a mummified ibis as a symbolic gesture to the god Thoth. So there are millions of these things. This is just one example of them. But this particular mummy, as you'll learn at this exhibition, it was found in a closet in Goldwin Smith Hall. There was a professor that was retiring or had died. I can't remember the exact story. But in any case, his office was being cleaned out. There was a mummy in a shoebox. The custodial worker called the archaeology department and said, "Hey, do you guys want this mummy?" Yeah. They had no idea what was in it. It's often the case because there was such an economy of ibis mummies, there are a lot of fake ones. Ones that you wrap it up and there's actually nothing inside of there. And then, you know, some ancient Egyptian swindler would sell you, yeah, this is an ibis mummy. No, it's not. So it wasn't actually obvious that there was anything in here. So they took it to the vet school and got it CT scanned. This is the CT scan. You can see the ibis head here and its long beak, like that. So it's all folded up inside of this mummy. And then since then, Carol Ann has been trying to figure out, to piece together the history of this thing. Where did it originate from? How did it get to Cornell, this whole sort of provenance of this thing? One of the interesting pieces of data that will be coming in the next couple of weeks is a veterinary ophthalmologist, someone who specializes in eye surgeries. So you can imagine the sort of tooling that you use to do an eye surgery is very, very small needles and such. They did an endoscopic surgery on the mummy to go in and extract tissue from the interior, some feathers and bones and stuff. And then that was sent off to a DNA lab to get sequenced, which will hopefully help narrow down the exact age of this thing and its specific place of origin. It likely came from one of two temples. Apparently, I have come to learn there are two temples with millions of these things. It's likely from one of the two. And amazingly enough, there is a database of ancient ibis mummy DNA from these two sites. So getting this sequence will help narrow down its exact age and where it came from. Incidentally, it might be 2,000 years old or it might be as old as 5,000 years old. So the uncertainty in this age of this thing is measured in millennia, which is just bananas. But it's on display in Upson Hall. You should go check it out. Yeah.
How much money is it worth?
Oh, I don't know the answer. It's priceless. I don't know the answer to that. Okay. Anything, how are Boids wrapping up for folks? Anything that folks want to talk about Boyd related? Any optimizations that people want to talk about? I know you're kind of giving away the goat here a little bit with the Friday lab section yet to check out. We'll talk about that next week, I think. Maybe we'll go through and folks can share their various optimizations. I've seen some good cheats. The most Boids I've seen so far is you guys, which was what, 3,600? 3,600, there was a lot of cheating involved, but the illusion holds absolutely. The behavior of the flock looks like the behavior of a flock that is obeying sort of the canonical set of rules. It doesn't look like they're cheating in any way. So you get away with it. As long as it looks right, it is right. So for the time being, 3,600 is the number to beat. Yeah?
So the judgment is purely visual?
So the one hard and fast rule is it has to be 30 frames a second. That is, you can't cheat that. But then the judgment beyond that is, I'll ask for you to set up the box boundary conditions, and we'll watch the flock for a while. And yeah, it's just essentially a subjective, sort of subjective, but does the illusion hold? Does it look organic? And your brain knows if it does or doesn't. So we'll look at it together and figure it out. And the other thing I'm kind of looking for is, I want for the flock behavior to look like the flock behavior that we demonstrated in here. If you cheat, you might get sort of more chaotic flocks. And in the event that you do some cheats that leads to an emergent flock behavior that's different than the one that we presented, I'll encourage you to play with the parameters until you can recover the flock behavior that is desired. Any other Boids questions? Incidentally, Bruce and I were kicking around a few more final project ideas. We're wondering, is it possible, do you think, to, so sound time of flight on a system like this is pretty simple, actually, because sound moves slowly as compared to the speed of the microcontroller. Could you measure light time of flight? If you build a range-finding device that maybe you have some super fast rise time light source, you shine a beam of light out, it reflects off of some surface and comes back and hits some super fast rise time light receptor that interfaces probably with a PIO program, so that you could count the number of CPU cycles between emitting the light and receiving the reflection back. Could you build an optical rangefinder using that kind of a setup? I think it would be hard. It would be an awesome project for folks that are interested in time optimizations, really, really precise time. Getting into that kind of mindset, it'd be a really fun project to maybe try to undertake. Because in principle, I think you could measure ranges to within like 2 feet or so, supposing that your rise times were all fast enough. An interesting thing to try. The other thing that we were thinking could be fun is, if there are any folks here that are sort of interested in physics or the history of physics, could you measure the speed of light using the Raspberry Pi Pico somehow? Maybe you get some big coil of fiber optics and you shine light into one end and measure the amount of time that it gets to the other end. And again, with some fast rise time equipment, maybe you could get a sense of the speed of light. Could you set up some version of one of the famous historical experiments that you read about to measure one of the fundamental constants? Could you figure out some experiment that you could set up to measure Newton's gravitational constant? I don't know. For a particular personality type, that might be a really fun flavor of project. So you can make sort of a modern version of a classic physics experiment. So I don't know, something to mull over, I suppose. Any final project stuff people want to talk about? Anyone have a sense of what they want to do?
We don't want to share it so that...
You don't want to share it? It doesn't matter. People can do the same project.
Then it's a competition. Yeah.
Oh, no, it's not. Okay, then unless folks want to talk about anything related to Boids or anything related to final project ideas, I think it's about time we start talking about Lab 3. So my plan for today and Wednesday of next week, since we have off Monday, and probably into Friday, is to go over the content that's going to be relevant for your first week's checkout in Lab 3. So let me just start by giving you a reminder of what Lab 3 is. Just talk through this at a high level for a moment. So, like I talked about in the beginning of this whole class, each of these lab assignments aims to achieve a bunch of different criteria. One of the things that I try to do with this whole sequence of lab assignments is appeal to students in this class with a variety of interests. So, if you're interested in digital signal processing and audio synthesis, Lab 1 is kind of for that set of personalities. For the optimization interested folks and people interested in computer graphics, Lab 2 is sort of geared towards them. And then for the more robotics inclined people, Lab 3 is sort of pointed at these folks. And the hope is to present each of these different things sort of in their best light, so that, you know, even if you think you're really interested in visual signal processing and not a big fan of robotics, well, hopefully this is a fun enough robotics project that you find it interesting. So the challenge in this lab is going to be to balance an inverted pendulum, which is sort of a classic controls problem. If you take a feedback controls course, you will absolutely talk about balancing an inverted pendulum. We're going to do a twist on this problem where the sort of classic way to balance the pendulum is to move the base. So you can imagine having a stick on a little cart that's on a track, and the classic problem is how do we move the cart back and forth in order to keep the stick balanced, like a Segway robot or something like that. We're going to do something slightly different, which is the base is going to remain fixed, and we are going to keep the pendulum balanced by moving a reaction wheel at the top of the pendulum. Doing this for a number of different reasons. One, I think the physics is really interesting, and I think it leads to an interesting version of this problem. And also, it's a lot more manageable in the lab because everything remains stuck to where it is, so we don't have things running around on the lab floor. So there's a bunch of stuff going on in this lab. In order to get this to work, we first of all need to know what is the present angle of the pendulum so that we can move that angle back to where we want it. So say 0 degrees is straight up. We need to measure the present angle of the pendulum so that we can move it from 5 degrees back up towards 0 degrees. So we need to have some sort of sensor in the loop in order to actually figure out what's our present pendulum angle. The sensor that we're going to be using is an inertial measurement unit. So this is an integrated circuit that includes both an accelerometer and a gyroscope. And we will be synthesizing data from both those sensors in order to generate an estimate for the current pendulum angle. You might ask, well, seems like you could just get that answer with the accelerometer, right? You know that gravity is always down. So if we're tilted like this, we get the measurement out of the accelerometer and there's like a cosine involved or a sine involved, and you could just compute the present pendulum angle. Why isn't that sufficient? People have a sense of this? What you will discover when you put this together and start playing with it is that accelerometer gives you really noisy measurements, quite noisy. The error out of the accelerometer is unbiased, which is to say the noise bounces around the true angle of the pendulum, but it bounces around quite a lot, particularly once the motor starts turning. Once the motor starts turning and introduces vibrations and excitations into the pendulum arm to which the sensor is attached, what you'll see is that your estimates of the angle as determined directly from the accelerometer get crazy noisy. Too noisy to close a controller around. It wouldn't work. So we have to supplement our angle estimate from the accelerometer using the gyroscope. So you might consider using only the gyroscope to measure the pendulum angle. So you could say, I'm going to hold the pendulum perfectly straight up when I click go, and then I'm going to measure the gyroscope, which is giving me a rate measurement, so something like radians per second. And I'm going to integrate that so that I maintain knowledge of the current position of the arm. What's the problem with just doing that? It drifts. I said that wrong, drifts. We'll see this too on the VGA screen. What I'm going to ask for you to display is the angle estimate as determined directly from the accelerometer, along with the angle estimate as determined directly from the gyroscope, along with the angle estimate as estimated by a complementary filter of both accelerometer and gyroscope measurements. And what you'll see is that the accelerometer angle measurements are messy. The gyroscope measurements, they're very responsive, but they drift. They accumulate a ever-increasing error over time. And a appropriately constructed complementary filter of the two sort of maintains the best of both worlds. It remains largely unbiased, which is to say you're not accumulating an error bias as the system runs, but it has significantly less noise than the accelerometer measurements. So we're going to be using what's called a complementary filter, which is essentially a strategy by which we high pass the gyro estimates and low pass the accelerometer estimates. Right? So the responsiveness of the gyro, we utilize that by high passing it, but by low passing the accelerometer, we maintain the zero mean feature of the accelerometer error. What you'll find is it's super easy filter to implement. It gives you really nice results. There are examples of filters that will give you better estimates. Kalman filters, for instance. You could get a better estimate from a Kalman filter. They're a little trickier to implement. This is sort of quick and dirty and works. It's a good one to know, actually. It's a nice one for the repertoire. So we'll be estimating angle using a complementary filter of accelerometer and gyroscope measurements. That's going to be a part of your week 1 checkout. It's getting that to run. And the demo code provided just puts the raw measurements onto the VGA screen. So you'll be taking those raw measurements, putting them into a filter, and then putting the filtered estimate up along with the raw measurements. So that's all sort of the sensing side. And then the other aspect of this lab is, okay, once we measure the pendulum as being at a particular angle, we want to move it back to the angle where we want it, which is straight up. And we're going to do that by modulating the speed and direction of this wheel. You can imagine that by modifying the speed and direction of that wheel, what we're playing with is the angular momentum of the system. You may remember from physics, I don't know, your first physics class here, probably torque is dl dt, right? Torque is equal to the change in angular momentum. So as long as we're changing the angular momentum by changing the speed of this wheel in one direction or the other, we're exerting a torque on the system that we can use to rotate the whole thing back to where we want it. There's some puzzles to solve here, though, because as many of you are likely aware, and as we'll talk through today, we are controlling this wheel with a DC motor that's hooked up to an H-bridge. What's scary about DC motors? Why do you have to be careful with DC motors when you're hooking up electronics? That's an ill-formed question. Yeah?
Noise?
Yeah, they're crazy noisy. We'll look at this today. They kick up an unbelievable amount of noise that could, at best, it could do things like mess up your measurements, and at worst, it can actually damage other components of the circuit. So the way that we protect the microcontroller and our sensors from the noisy DC motors is we completely electrically isolate them. So if we have time today, I think we will, what we'll talk through is the circuit that you'll build to electrically isolate the DC motor from the microcontroller and your sensors. And by electrically isolate, I mean that they don't share power and they don't share ground. They are two truly independent circuits. Then how do you get the two to talk to one another? You need some mechanism of communication that isn't electrons, right? So what we'll use is an optical isolator. It's a little integrated circuit that includes inside of there's a little LED that emits photons, light, and then there's a phototransistor that receives that light and turns on or off based on whether or not the LED is off. So this is a mechanism by which we can have the microcontroller circuit, which is a totally different circuit, different power, different ground, control the DC motor circuit, which has its own power and own ground, but it won't do so through any electrical connection. It'll do so purely through light, which protects all the stuff on the microcontroller circuit from the crazy noise being generated on the DC motor circuit. We're also going to build that circuit with some components to help mitigate that noise, and we'll talk about that. But that's going to be the fundamental idea. And an unexpected but kind of nice feature of this lab, and particularly of this sensor, is it's really sensitive to noise. If you do not properly isolate this sensor from the motor, it freezes and doesn't come back alive until you reset it. So you will know whether or not you are properly isolating the microcontroller and the sensor from the motor, because if you are, you're going to be getting measurements out of the sensor. And if you're not, it will just stop giving you measurements. And that is your indication that you have to think more carefully about electrical isolation, which includes all the stuff that I've talked about. What it also includes is a consciousness of physical layout of your system. If you have the wires that communicate to your motors physically nearby the wires that are communicating out here to the sensor, physics will couple them, right? So you can have your noise being introduced. You can set up your circuit just right, but if you set it up without being conscious of the physics that can happen between adjacent wires, you can still have too much noise coupling across into the sensor circuit, and the sensor will stop. So I love this lab because, to the extent that this is a cumulative design experience class, a CDE course, what I am supposed to do in this class is come up with labs and exercises that synthesize as much of the undergraduate curriculum as possible. Boy, does this do that. And it does so in a way that you just can't get away from. So getting this whole system to a state where you are in the position to be tuning it to balance is really instructive. There's a lot of thought that has to go into that. And then actually getting it to balance. Once you get it into that position, getting it to balance, if you've built your user interface thoughtfully, so what you are asked to do is build a user interface that allows you to change the parameters for your PID controller dynamically. So you can say, change the proportional gain to this, change the integral gain to this, without resetting the system, so that you can really quickly tune this thing. So once you get the whole thing built, the last task will be playing with this controller until you can actually get the thing to balance. Which, by the way, is hard. This is a relatively short arm, which means it's pretty hard to balance, right? So it's going to be a challenge to actually get this thing to balance, and depending on how successful people are or aren't at getting the thing to balance, maybe it'll be the case that if you get it to balance, that's bonus points. Maybe, I'm not sure. I have to get a sense of precisely how difficult folks find it to actually balance this thing. But in any case, we'll give it a go. Any questions about the sort of the overall goal of this lab? So they're going to have your microcontroller. It's going to be controlling these DC motors and listening to these sensors. And then you're going to have a real-time VGA display here that shows you things like your estimated pendulum angle and your control input. And one of the first things that you'll be asked to implement is this VGA interface, because it's critical for debugging. It allows for you to actually see what action your controller is taking in response to particular arm angles. Yeah?
So our control input just voltage to the motor, or?
What your control input will be is, so we want to be able to control both the speed and direction of the motor. So the motor is going to be driven by an H-bridge. Your control input will be a pulse width modulation duty cycle to, each of the two inputs of the H-bridge to control the speed in either direction.
So no encoder?
No. Mm-mm. One of the things that makes this hard or different is torque comes from dl/dt. You only get torque when you're changing angular momentum. So if this wheel is spinning at a constant speed, you're not exerting any torque. You only get torque when you're changing the speed of the motor. It makes the controller design really interesting. So suppose you're tilted off a little bit and the motor's just spinning away. If it keeps spinning at a constant rate, it just falls right over. So if it's tilted off a little bit, it has to speed up until it comes back up to the top. And then it has to slow down appropriately in order to stay balanced at the top. And it takes some work, but you can get it to work. And then the fun test to run then is you run up and you smack it with a pencil and you see if it can withstand the little disturbances and rebalance itself. It kind of does. Let me just play this video. Let's see here. All the way around the outside, there are little holes that can accommodate 1032 screws. So if you want to be able to generate more angular momentum, you can increase the weight of the wheel. So that's more tuning that you can do. You can tune the mass of this thing as well. This whole thing, by the way, I'll just mention, this wheel is designed and printed by Smith, Charles. Yeah. So, and then the other pieces here are this base. You'll be asked to build the base as well. The base is just made out of Legos. So I have a whole bunch of Legos in the lab so that you can build a base. The size of the holes in the Legos are perfect for 1032 screws. So you'll build a little base out of Legos, and then a long 1032 screw will go through the Lego base, and you can slip the acrylic arm through. There's a hole that could accommodate that screw as well. So you end up with a relatively low friction hinge for the arm. And then you can put a little nut on the back to just secure it in place. And then each of you will use a pair of these quick grip clamps to hold the Lego base to the table. And those clamps double as rotation stops. So in this lab, I will get out very, very large buckets of Legos, which incidentally, I feel like it's just a nice thing to have in the lab anyway, because for mechanical design projects, they're kind of awesome. By the way, some of you, might look at this and, why go to all this effort of using a complementary filter to get rotation angle? Why not just attach this thing to a potentiometer? Still have a sense of why that? I tried this. Why didn't that work?
Was it giving like a lot of feedback?
It was the range of angles that we're trying to control here is so small that the range over which the potentiometer was varying was quite little. So it was difficult to get useful angle measurements out of it. Now, some of you in here are mechanical engineers, and when I say that, you're screaming, gears, use gears. I tried that too, and I couldn't get that to be low enough friction. So this is the solution that we ended up going with, and I'm actually kind of happy with it because then we have to do complementary filters, and that's a useful thing to add to the repertoire. Okay. So let's talk about, I want to talk about this is the circuit that you'll be asked to build to drive the DC motor. So there's two optical isolators here with a pair of resistors, and they are used to drive the two inputs of a H-bridge motor driver that control a motor in either direction. Then we have a bypass cap here. I want to just show you this so that you know where it lives. But I want to sort of take our time to talk through why each of the elements of this circuit is necessary and what it's for. And really what a lot of the stuff in this circuit is here to do is to mitigate the noise coming out of these DC motors. And I think the best way to discuss why and how these things mitigate that noise is to understand the nature of the noise that's being generated, which means a brief conversation about how DC motors actually work. What is the internal mechanism of the DC motor that's generating this noise? What are the properties of the noise? And so why does this work for mitigating that noise? So in order to do that, I wanted to just show you a few slides. So how's a DC motor work? There are a few different flavors of DC motor. There's brushed DC motors, brushless DC motors. What I'm going to talk through today, just as an example to talk through, is a brushed DC motor. What's going on inside of a DC motor is we have some pair of permanent magnets that's setting up a static magnetic field. And then inside of this magnetic field, there's a loop of wire called the armature through which we put some current. And you'll remember from one of your first physics classes that if you have a loop of wire carrying current in a magnetic field, you get a torque on it, right? There's what is the Lorentz force, right? It wants to rotate this thing to align it with the field. So this, we put some current through here. It starts to rotate in order to align with the what's called the stator field. And then as it rotates, this device here that's called the commutator is a device that exists to solve a problem, which is we need for this armature here to be rotating. if we just communicated that armature with wires, clearly they would just twist themselves up, right? So we need some mechanism by which we can maintain an electrical connection to a rotating thing here. And the commutator is what accomplishes that. So generally, this armature is sort of spring-loaded against the commutator. The commutator in a brushed DC motor contains a whole bunch of little conductive brushes against which the armature will slide. And you can see that there's little gaps in this commutator so that as this slides 180 degrees, the direction of the current through this armature swaps direction so that it rotates up and then the current swaps direction, and that keeps the torque going to keep it going in the same direction. If we wanted it to rotate the opposite direction, we would just supply current in the opposite direction to this armature commutator system here. Anything else to mention about this? So you can imagine, sort of interestingly, you can imagine that when the commutator is in this configuration, there's quite a lot of torque, right? As this rotates so that it's more aligned with the stator field, you get less torque. So if you plot the torque coming out of a DC motor, you'll see what's called torque ripple. The amount of torque coming out of the motor will ripple up and down, and it's because the amount of torque on the commutator is a function of its orientation. So as it rotates, the torque decreases, increases, decreases, increases, and so on. So the other thing to just mention in connection with DC motors is back EMF. This commutator, it's a current carrying loop of wire that's rotating in a magnetic field. That is a generator, right? So we are applying some current to this armature in order to get it to rotate, but then as it rotates, there's current that's being induced back onto the armature in the opposite direction, right? So we put some current through here, it starts to rotate. As it rotates, current gets induced in the opposite direction that fights back against the current that we're applying. So the model that we use for a DC motor, which we'll look at in a moment, is usually, if you have the schematic symbol for a DC motor in your circuit, you can pretty reasonably replace that schematic symbol with a resistor in series with an inductor in series with a generator. The resistor is there because there's some resistance through this whole system. The inductor is there because these DC motors have loops of wire in them that carry inductance, probably something on the order of like a millihenry or something like that. And then the generator is there because as this thing rotates, it behaves like a generator. It's generating a back EMF that's pushing current in the opposite direction, in the direction opposite that we're applying it. But this back EMF, it acts like a feedback mechanism. So you could imagine, so when this thing is spinning at a constant rate, the back EMF is about equal to the applied voltage. Suppose that we had a DC motor that was happily spinning and we grabbed the armature to slow it down. What would happen in that case is, well, all of a sudden, the armature isn't spinning as fast, so we can send more current through the armature, and as a consequence, we get more torque out. So you grab the armature of a spinning DC motor, the speed decreases and the torque increases. Likewise, suppose that you've been squeezing it for a while, it's going at a constant rate, and then you let go. All of a sudden, this armature is spinning faster, you're generating more back EMF, so you get less torque and more speed. So it's an inbuilt sort of torque regulation mechanism, this back EMF. Okay, so like I said, this is our approximate model for a DC motor. A DC motor looks kind of like a resistor in series with an inductor in series with the generator. Why is it creating all this noise? Well, let's think about the inductor, the inducting element within a DC motor. You'll remember, again, from a class a long time ago, that the voltage across an inductor is given by L, the inductance, times di dt, the change in current through the inductor. L in the case of a DC motor is, I don't know, probably something on the order of a millihenry, maybe, something like that. But suppose that you're driving a DC motor with a pulse width modulation signal like we are. Then you are really rapidly turning current through that DC motor on and off, right? How rapidly? I don't know, maybe like tens of nanoseconds, really fast. So your di dt, the dt there, the time over which you're modifying the current through that inductor is really short. And the current that you're turning on and off can be quite high. These DC motors, I was spinning one in the in my office before I came here just to get a sense of this, and just a little silly drone motor of the sort, I don't know, costs like a quarter, pulls like half an amp. Right? So they can pull quite a bit of current. And if you're driving them with a pulse width modulation signal, you're turning that current on and off very quickly. So your di dt is huge. So what you end up with coming out of this thing is really, really large voltage spikes that you have to protect the rest of your circuit against. And I have just a little demo of this. Let me just see here. So let me mute this. So all that's happening here, this is a scope trace of me just applying voltage to a DC motor and using the scope to measure the voltage across that motor. And what we're seeing, what we were seeing, is really, really big spikes in voltage in both directions, opposite polarity voltage spikes, right? So we have to deal with this, or this is going to potentially damage a lot of stuff, right? So one of the mitigating strategies, right now what I'm doing is plugging in a bypass cap, and when I do, you can see that the voltage spikes go shoop. You get attenuated considerably. So one of the strategies for mitigating these large voltage spikes coming out of DC motors like this is some sort of a bypass cap that allows a path to ground for these really, really fast spikes in voltage. So that's why this is here. The other thing that you'll often find in a motor circuit, a DC motor circuit, is a snubber diode, because you can imagine that when we turn off, when we open a switch to the motor, the polarity across the motor switches direction, right? Because this is acting like an inductor. So you open this circuit, this becomes the high side, this becomes the low side. We have to be conscious of this. So usually, the component that we put in place in order to protect the rest of the circuit against those big reverses in polarity across the DC motor is a snubber diode. So this is a diode that is oriented such that current can only flow from what is typically the low side of the motor back to what is typically the high side of the motor. But what this does is when we open the switch to the motor and there's a big reverse in polarity across the motor, it allows for a safe path for that current to follow that protects the rest of the circuit. So typically in a motor circuit, what we'll find is probably a bypass cap to mitigate the really high frequency noise, and probably a snubber diode to mitigate the high voltage spikes that are opposite polarity. Usually you'll find these two things. But even so, if we go back to that video, even so, you can see that even with the bypass cap in place, there's still quite a bit of noise there, right? I mean, there's still a lot of stuff here that we want to protect the rest of our circuit from. So be careful, electrical engineer will completely electrically isolate the motor from the microcontroller and from sensors. And the way that we do that often is with one of these optical isolators that I was just talking about. So we'll talk through the details of this circuit. Do we have time to today? Yeah, we have some time. But like I mentioned, what we're looking at here, let me pull up the other web page here. So this is the circuit that you're actually building. By the way, what's missing from this circuit that we just talked about?
Diode.
Yeah, the snubber diodes. They're actually built into the H-bridge motor driver that we're using. So we don't have to include those. This has inbuilt snubber diodes, which is kind of nice for us, I guess. Okay. So that's why we see this bypass cap here. Ordinarily, like I said, we would see a snubber diode here as well. That's built into the L9110 H-bridge motor driver that we're using. So okay, those snubber diodes exist in there. How about these things? So these optical isolators, as I mentioned, it's a little integrated circuit, so it just looks like an integrated circuit. But when you look at the pinout for this thing, it describes an internal mechanism that includes an LED and a phototransistor. So you will use the Raspberry Pi Pico to send a pulse width modulation signal to the LED to turn it on and off at whatever duty cycle it is that you want to drive the motor. That turns on and off the phototransistor, which feeds one of the inputs to the motor driver, so that by playing with the pulse width modulation signals that you send to each of these two optical isolators, you are affecting the pulse width modulation signal that you're using to drive the motor. Make sense? What are these two resistors for? This one here, so this is about a mega ohm resistor. When we turn the LED on, this transistor is turned on by sending some current into its base, right? So we need the current to leak off that base if we want to be able to turn it off and on at the bandwidth that we desire, right? It's this resistor that controls the bandwidth of this optical isolator. How quickly does current leak off this base? If this were too low, suppose we made this resistor too low, the effect of that, I believe, if you think about this, would be that we'd never be able to turn the optical isolator on because we wouldn't be able to generate enough current into the base. We'd be leaking it out down here. Alternatively, suppose we made that resistor much too high, then we wouldn't be able to turn it on and off at the frequency that we want to. The current wouldn't leak away fast enough. Something like a mega ohm is about right for us. We're going to drive these at 1 kilohertz. So your pulse width modulation signal will be going at 1 kilohertz. Pretty slow, right? So this is what sets the bandwidth. And then we have a 10K resistor here, just so that when we turn this on, we aren't shorting VCC to ground, right? So we have a 10K resistor here, and above that 10K resistor is where we feed the motor driver. We have two of these, two identical copies of these to drive each of the two inputs to the motor driver. Yeah.
So the signal is PWM, right?
Yeah.
Modulation. So that effectively still works with the phototransistor transition. It's not like a weird analog conflict.
It does still, as long as you're driving it inside of the bandwidth that's allowed by this resistor, then you can scope this junction here, and you will see a copy of your pulse width modulation signal that you sent in with different peak-to-peak voltage, because we're powering the motor at 5 volts and the Pico's running at 3.3 volts, of course. But this brings up a good point, which is when you're putting this circuit together, do not build the whole thing and then test it. Instead, what I would recommend is build one of these optical isolator circuits here, generate a pulse width modulation signal using the function generator. You don't even need the Pico involved. There's a function generator at every bench. Just generate a 0 to 3.3 volts peak-to-peak square wave, at about 1 kilohertz. So send a PWM signal into this optical isolator from the function generator. Set up these two resistors here and scope the output, and just make sure that you're seeing a PWM signal in the output. So test one of the optical isolator circuits in that way, then build the other one and test that one, and then add in the rest of the stuff. Then add in the H-bridge and the motor and so on. Otherwise, it can be tricky to debug this thing. The other thing I'll really encourage you to be mindful of in this lab is breadboard discipline. So I would encourage you, in this lab in particular, to not use the jumpers that you were all provided, but instead go to the back corner of the lab and cut wire to size, strip it yourself so that you have a nice, neat breadboard. It makes it so much easier to debug this thing. Makes it easier for you, and then in the event that your circuit has a bug and we have to figure out what the hell's going on. It makes it a whole lot easier for me and Bruce and your TAs if you've used good breadboard discipline so that the connections are obvious. Makes it a lot easier to put a scope probe, in strategic places and stuff like that. So really try to exercise good breadboard discipline in this lab.
Can we just solder the wires and stuff on the?
Use a solder board?
Yeah.
No. For a final project, yes, sure. If you end up incorporating a circuit like this in your final project, then I think it's a good idea to use a solder board. For the lab, when we want to be able to take things apart and put them back together again. No. Okay. Any other questions from folks about this?
Can I ask a question on sensors?
Yeah.
So when we build the low pass and the high pass filters, how are we gonna decide the cutoff frequency in the order of the filter? Is there like a recommended setting, or we have to figure out our own?
There are recommended parameters for recommended values for all parameters in this complementary filter. That said, you might do a little bit of playing with it. What you'll find is, is there anything good here to show you? Let's just see. Let me play this and while I talk about it. What you'll find is the two parameters that you can play with is, it's kind of nauseating. To what extent, what amount of weight do we give to the accelerometer measurements and what amount of weight do we give to the gyroscope measurements? And it perhaps stand to reason that you could, if you cared to, give 100% weight to one or the other, in which case the complementary filter output, which is the green trace there, would just be right on top of either the white trace, which comes from the accelerometer, or the red trace, which comes from the gyroscope. Incidentally, what you're seeing there is the gyroscope biasing. It's accumulating error as we go. And you're also seeing the noise on the accelerometer measurements. And then the green is the complementary filter of the two. So you can see that for this demo, I have an accelerometer weight of 0.001 and a gyro weight of 0.999. We're really, from update to update to update, we're really heavily weighting the gyro. If we were to weight the gyro a bit more and the accelerometer a bit less, what we would see is a little bit more bias in the complementary filter output, but less noise. If we were alternatively to weight the accelerometer a little bit more and the gyro a little bit less, we would see this green trace move up towards the accelerometer output, that is to say less bias in our complementary filter output, but we would also have less noise. So it's a trade-off. What you're trading in this case is bias for noise. And you're playing with this until you find a balance that you're okay with. Not that necessarily you're okay with, but that works for your controller. And I have a recommended value for you to use, but it's an interesting thing to just mess around with to see, what different settings get you. Yeah, so in this case, you can see I've dropped I am now listening more to the accelerometer and less to the gyro, and you can see that the green trace is now more comfortably sitting on the accelerometer outputs. There's less bias, but it's a little bit more noisy. It's hard to see, but it's a little bit more noisy than it was before. So I think something like that setting is probably perfect for the lab. About 0.99 gyro, about 0.01 accelerometer. Yeah. Other questions? So what I want to talk about next time is I want to talk in I think a lot more detail about this complementary filter. And then we'll talk a little bit more systematically about a recommended order of operations for a recommended order in which you should complete things for the week 1 checkout. The easiest way to move through those tasks. Okay, there's a lot of reading for this lab. You might consider reading up on this lab, when you've got the time.